To transform an exponential equation into a logarithmic equation, you just reposition the base b, exponent x, and overall numerical value n such that b to the x equals n transforms into log base b n equals x. A logarithm is just a missing exponent. We're used to seeing exponential form, this b to the x equals n form. Let's practice a few translations. We're going to start out going from exponential to logarithmic, and then we'll do a couple the other way. The exponentials you're very familiar with. For example, 7 squared is equal to 49. A couple of 7s multiplied together gives you 49. Written as a logarithmic equation, your base number 7 becomes a subscript. Your numerical value 49 becomes the n value, the numerical value. And your exponent 2 is what your logarithm is equal to. So it really is just repositioning bxn, bxn, bxn. The way you interpret a logarithm is what a logarithm is equal to is the exponent that it takes to get the base number equal to the numerical value. 7 to what power is 49? Squared. Very good. The example to the right, base 3, numerical value 1/9, exponent -2. So this exponential equation in logarithmic form is log base 3 of 1/9 equals -2. Going the other way, we're going to take logarithmic form and go back to exponential form. Log base 5 of 125 equals 3, and that's because 5 cubed equals 125. 5 cubed equals 125. In the other logarithm, log base 2 of 1/8 equals -3, and that's because 2 to the -3 power is equal to 1/8. Just keep in mind that a logarithm is an exponent. Now, log base 4 of 16 equals something. It's helpful to translate a logarithmic equation into an exponential equation if you need to. Now, if you keep in mind that we're just looking for the power of 4 that's equal to 16. So 4 to the x equals 16. 16 is 4 squared. Once you get a common base number, and if you'll remember from a couple videos ago, this is a one-to-one property of exponents. If the bases are equal, the powers have to be equal. In the next example, log base 9 of 3, we're trying to find out what that's equal to. Well, in the first example, we knew that 4 squared was 16, so our answer was 2. It's harder to tell what power of 9 you got to have to make it 3. So let's translate. 9 to the x power is equal to 3. 9 is 3 squared, so I'm going to rewrite 9 as 3 squared. That x that's already in the exponent, it'll just join up with the 2. 3 by itself is 3 to the first. Same base. That means 2x has to equal 1. And that'll happen if x equals 1/2. In the last slide, we're going to discuss this a little more formally, but if you ever get in a pinch on needing the value of a logarithm, and it's one of these that's a little bit harder to figure out, you can type in log of the second number over log of the first number. So in this case, it'll be log of the n value 3 over log of the b value 9. Log 3 over log 9. You have to press the log button twice. Don't forget to hit log again for your denominator. Logarithms have one-to-one property as well. If 2 logs are equal, x equals y. In the first example, we have log base 5x plus 1, log base 5 of 3. Same logarithm, that tells us x plus 1 has to equal 3, and that's true if x equals 2. At the top right, log base 3 of x minus 4 equals log base 3 of 1. Same logarithms, x minus 4 has to equal 1. Add 4 to both sides, and that is true when x equals 5. The example at the top left, a log without a base written is an understood 10. Like a square root, you don't ever see the 2 written. With a common log, you don't have to see a 10. It's not wrong if you write it, it's just a lot of times it won't show up. Same logarithm, that means x squared plus 5x has to equal 24. Because this is a quadratic, I'm going to bring the 24 over, change its sign. We need two numbers that have a sum of 5 and a product of negative 24. We made a list of factors of 24 in class, and we decided that a negative 3 and a positive 8 would get the job done, and it does. If you add negative 3 and 8, you get 5. If you multiply negative 3 and 8, you get negative 24. This factor is 0 if x equals 3. This factor is 0 if x equals negative 8. You can check by substituting. Put in a 3, this comes out to 24. Sub in a negative 8, it also comes out to 24. Both values of x are good. Upper right example, natural log of x minus 2 equals natural log of 7. Now this first upper left log, you didn't have a base, it was an understood 10. If you see ln, that's log with a base e. X minus 2 has to equal 7, and that'll be true when x equals 9. So you have common log, natural log. Those are two special logarithms. And then our final example for this slide, we have natural log of x squared minus 3 equals natural log of 18. Same logarithm, that means x squared minus 3x has to equal 18. Move 18 across, change its sign. X squared is x times x, and now we need two numbers that have a sum of negative 3 and a product of negative 18. And you guys were really quick in class to tell me that that is positive 3 and negative 6. If you add these numbers, you get negative 3. If you multiply them, you get negative 18. This first factor is 0 if x equals negative 3. The second factor is 0 if x equals 6. A quick substitution, negative 3 checks, it comes out to 18. Positive 6 substituted in, also comes out to 18. Both answers are good. And on our last slide, change of base formula for logarithms are really helpful, especially when you have a logarithmic expression where you don't have an exact power. On the previous slides, we did a couple of examples where we had 7 squared equals 49. Log base 4 of 16 was equal to 2 because 4 to the second power was 16. There are times when you can't come up with a nice whole number exponent, and that's okay. Here's our backup plan. For any logarithmic expression, log base b of some numerical value, you can either press your log button, log n over log b, or you can press your natural log button, ln of n over ln of b. Either one works, just commit to the same button on your calculator both times. Let's look at how this does come in handy. Log base 4 of 100 equals something. In the light blue at the bottom of your screen, I tried out different powers of 4. 4 to the first is 4, 4 squared is 16, 4 cubed is 64, and 4 to the fourth is 256. We never did land at 100 exactly. So what we're really after is the power of 4 that's equal to 100. Well, we can tell from down here, it's not going to be a whole number because 4 cubed comes up short of 100, and 4 to the fourth goes too far. Using change of base, log 100 over log of 4, log 100 over log of 4 is 3.322, and that's rounded to 3 decimal places. If you check and you do 4 to this power, you get real close to 100. And remember, with a logarithm, the idea is to find an exponent. It's the exponent that takes your base to the numerical value. 64 is short of 100. 256 is more than 100. And it makes sense that our answer is going to be between 3 and 4. In the upper right logarithm, we want to know the power of 7 that equals 60. 7 to the first power is 7. That's not enough. 7 squared is 49. That's not enough. 7 cubed, that's 343. That's too much. So our answer is going to be between 2 and 3. Using change of base, log 60 over log 7 is 2.104. 7 to this power will be real close to 60.